Let's move on to the next, laboratory preparation. How do we prepare alkenes in the lab? Now, alkenes are prepared through dehydration of alkanols. Okay, so what do I mean by dehydration? Removal of water from the alkanols. Now, in this case, we are going to need a dehydrating agent. Dehydrating agents are compounds that either remove water or elements of water, hydrogen and oxygen, from another compound. So in this particular reaction, we can use either concentrated sulfuric 6 acid or aluminium oxide. Okay, they can both do the purpose, but I want to say this. If aluminium oxide is used, not only will it act as a dehydrating agent, it will also act as a catalyst. It will speed up the rate of the reaction. So the general equations are as such. You start with an alkanol. This is an organic compound, by the way. It's going to be discussed in detail in Form 4. And by the use of either of these dehydrating agents, you end up having alkene plus water. Now let's imagine we have, a setup such as this. So the first step that you're going to need to consider is which alkanol are you going to use. Now bear in mind, the alkanol that is used should have the same number of carbon atoms as the alkene being prepared. Okay, let's make this short. I want to prepare ethene. Which alkanol am I going to use? Ethanol. What about if I wanted to prepare propene? Then I would use propanol. Butene, I would use butanol. So same number of carbon atoms. Whenever you see this prefix, F, but, meth, it refers to the number of carbon atoms that are present. So once I have that set up, and I want you to imagine I'm using concentrated sulfuric 6 acid, then what will happen is that the concentrated sulfuric 6 acid will dehydrate the alkanol. It's going to remove the elements of water from the alkanol. This is the structural formula of the alkanol. See that? So these two are going to be removed in order to form water. What do you have remaining? Let's look at whatever is remaining. C2H4. Boom! There goes your alkene, specifically ethene. So you're going to note that as the reaction progresses, there is effervescence. You're going to have a colorless gas being produced, which in this case is ethene. So the gas is then going to be passed through sodium hydroxide or potassium hydroxide solution in order to absorb any carbon 4 oxide or sulfur 4 oxide that have been formed. Okay, let's pause there. Where is the carbon 4 oxide and sulfur 4 oxide coming from? Now, in this case, we have the alkanol, ethanol. So on heating the ethanol, some of it will decompose, leading to the formation of carbon 4 oxide. So that is where the carbon 4 oxide is coming from. What about the sulfur 4 oxide? This comes from the decomposition of sulfuric acid on heating. So by passing through sodium hydroxide solution, you will be able to absorb these two gases that have been formed, ensuring that whatever you collect is simply ethane. Now in this setup, pieces of broken porcelain or sand are used in order to prevent bumping. This could lead to, cracking of the flask, and by using the sand, it will also ensure that you have uniform boiling of the mixture. So the ethene gas that is produced is collected over water because ethene is only slightly soluble in water. However, if you need the gas to be dry, you can use calcium chloride to dry it, okay? So calcium chloride is a drying agent. You can use it to dry ethene. But don't use concentrated sulfuric 6 acid because it will end up reacting with ethene. So, yeah. Now, moving on to the next bit, what are the physical properties of alkenes? Now, alkenes, just like alkanes, are colorless. So they are colorless gases, liquids, and solids. Now, they are slightly soluble in water. Actually, ethene is slightly soluble in water, and that is the reason why it's collected over water. Gases that are collected over water are either only slightly soluble in water, such as ethene, or insoluble in water. So coming back to solubility, ethene is slightly soluble in water. But when it comes to the rest of the alkenes, solubility in water decreases with an increase in the number of carbon atoms. So that means that as you keep on increasing the number of carbon atoms, solubility in water decreases. The rest are insoluble in water. But they are soluble in organic solvents such as benzene. Now moving on to the last physical property, this has to do with the melting and boiling points and densities. These increase with an increase in the number of carbon atoms. This is because of an increase in the strength of the intermolecular forces of attraction. Let's pause there. Over here, I have alkenes and the molecular formulas, okay? So, for example, the molecular formula of ethene is C2H4. Can we get its molecular mass? Yes. How are we going to do so? By simply summing up the relative atomic masses. So, relative atomic mass of carbon is 12. How many are there? We have 2. 12 by 2. Now, relative atomic mass of hydrogen is 1 by 4, giving us 4. Sum these and we get 28. Now, if we continue doing the same, we are going to get the following molecular masses. So what are you noting? When you look at the molecular mass, you are going to notice that as the number of carbon atoms increase, the molecular mass also increases. Now, when you have larger molecular masses, they tend to have stronger forces of attraction. You know, they have stronger van der Waals forces of attraction. So that means if you need to heat them such that they change state from either a solid to a liquid, melting, or a liquid to a gas, evaporation, you're going to need a lot of heat energy. And that is the reason why butene has a higher melting point than ethene. Okay? And the densities also increase. Now moving on to chemical properties. Now when it comes to alkenes, the chemical properties are quite many because alkenes are quite reactive. You know, they're more reactive than alkenes. And the reason for this is because of the presence of the double bond. So in chemical reactions, what happens is that the double bond splits. Now when it does so, it creates new bonds. And in these new bonds, you can have new atoms joining, leading to the formation of new products. So our first reaction has to do with combustion. Now alkenes burn in excess air to form carbon 4 oxide and water. So for example, ethene will react with oxygen to form carbon 4 oxide and water as such. If the air is limited, you know, it's not enough, what will happen is that the alkenes will still react with oxygen, but in this case, they are going to form carbon 2 oxide and water. In both cases, what will happen is that they burn with a yellow sooty flame, okay? Now, this is because of the high content of carbon that is present. Let's pause there. I want us to look at the molecular formula of ethene, C2H4. So, out of this, we are going to have the molecular mass of 28 grams. Okay, so how did we get 28? We simply summed up the relative atomic masses as we talked about previously. Now, out of these 28 grams, how much is, the carbon, the mass of carbon? 24. So 24 grams are from the carbon atoms. Each carbon atom has the mass of 12 grams and we have 2. So that gives us 24. So 24 grams out of 28 grams is simply carbon. If we were to convert this to percentage, we will end up having a percentage of 85.7%. Quite a high content of carbon, right? So because of this, you end up having alkenes burning in air with yellow sooty flames. They are yellow because you have, the carbon particles that are glowing and they are sooty because of the unburnt carbon particles. Now moving on to the next type of reaction that alkenes engage in. These are addition reactions. So addition reactions are a type of reaction whereby you're going to have a molecule or an atom being added onto another such that you end up having a different product, okay? So essentially you're adding one thing to another, addition reaction. Now, the addition reactions are possible in alkenes because alkenes have the double bond. So before any chemical reaction takes place, what happens is that the double bond splits to allow the formation of new bonds, and therefore new products can be formed. Now in the product, you're only going to end up having single bonds because the double bond was split to form a new product by the addition of something else. Now, under addition reaction, I'm going to discuss the following. Number one, self-addition. Number two, hydrogenation, halogenation, hydrohalogenation, reaction with bromine water, and lastly, reaction with acidified potassium manganate 7. So as stated before, these are quite a lot of reactions because alkenes are reactive. Why? Because of the double bond. So let's start with the first one, the self-addition reaction. So alkenes have the amazing ability of being able to react with other alkenes. Okay, let me make that clear. So for example, ethene molecules have the ability to react with other ethene molecules to form a larger molecule. This process is known as polymerization. So polymerization is the process whereby small units called monomers join together to form a large molecule known as polymer. So you're going to have one ethene molecule joining with another and another and another until you have a polymer. Okay? So what happens exactly? Number one, the double bond is split, creating three single bonds, which allows the addition of more molecules and more molecules and more until you end up having this long chain filled with ethene molecules. So ethene plus ethene, you end up having your polymer. So the polymer is referred to as polyethene. Now when alkenes form polymers, the prefix poly is placed before the polymer, okay? So for example, if I have propene, so the polymer of propene is going to be referred to as polypropene. If I have butene, the polymer is going to be polybutene as such. Sawa? Yeah. Now, for this particular reaction to take place, you need to have high pressures and high temperatures. Now, this is a process that is discussed in detail in organic chem too, okay? So when I get to that point, I'm going to discuss this in detail to your heart's content. But at this point, yeah, let it be so. Moving on to the next type of addition reaction, and that is hydrogenation. So in hydrogenation, as the name states, you're going to have alkenes reacting with hydrogen gas to form the corresponding alkanes. Okay? Now let me make it clear. We have ethene there, right? So if I open it up as such, there we have it. Now to determine what is the first step of reaction? Splitting open the double bond. So we are going to split it to have that. Now, as you can clearly see, we have two free single bonds. So this is where you're going to have the hydrogen atoms fitting in. So if we have this and we fit in two more hydrogen atoms, at the end, we have a structure that has the molecular formula C2H6. What is this, my dear students? This is ethane. So in hydrogenation, you're going to get an alkene reacting with hydrogen to form the corresponding alkane. So ethene with hydrogen gives you ethane. Propene with hydrogen gives you propane. Butene with hydrogen gives you butane and such. Now, this particular reaction, hydrogenation, has the following three conditions. Number one, high temperatures, specifically between 150 to 250 degrees Celsius. Next, high pressures of between 200 to 250 atmosphere. And lastly, a catalyst Now, there are actually two catalysts that can be used. You can use either nickel catalyst or palladium catalyst. Either is okay. Now, hydrogenation is a process that has a huge industrial application. Now, this is used in the manufacture of margarine. So, when hydrogen gas is passed through liquid oil, under these conditions that have been mentioned, solid fat is formed. Okay? So, this process is used in the manufacture of margarine through hardening of the oils. And it's through this process that we get products like Bluebird, Prestige, those. So we have hydrogenation to thank for those products. Kisha mnakaa mkisema, oh, how is chemistry important? How is this relevant to real life? Yes. Would we have Bluebird if we didn't have hydrogenation? No, we wouldn't. Now, moving on to the next one, halogenation. So as the name, indicates, we are having a reaction between alkanes and a halogen. It could be fluorine, chlorine, or bromine. So these two react with one another to form a haloalkane. So a haloalkane is simply a compound that contains carbon, hydrogen, and the respective halogen. So in this case, instead of us adding a hydrogen atom, such as in the case of hydrogenation, we are going to add a halogen atom. So number one, double bond is split open. And then if you have this particular reaction between ethene and chlorine atoms, what will happen is that the chlorine atoms are then going to fit into the three single bonds. And you end up having this compound. How are we going to name this compound? This compound is 1,2-dichloroethane. Why dichloro? Because we have two chlorine atoms. Where are they located? On the first and second carbon atoms. And it's ethane because F, we have two carbon atoms, A and E, we have single bonds. So we have single bonds throughout. So the name 1,2-dichloroethane. Now, what if I was to use bromine instead of chlorine? Same thing, double bond splits open, bromine atoms fit into the three single bonds. And you end up having 1,2-dibromoethane. So in this particular reaction, what observation are you going to make? You're going to note that the halogens, specifically chlorine and bromine, are decolorized. Now when it comes to halogens, all halogens are colored, okay? So for example, bromine is a brown liquid, chlorine is a green-yellow gas. But if they were to react with alkenes, they are going to be decolorized. So you're going to note that the colors fade, okay? It becomes colorless. And the reason is because these compounds that have been formed are colorless compounds. So essentially, 1,2-dichloroethane and 1,2-dibromoethane are colorless compounds, and that is the reason why you are not seeing any color at the end. You're seeing the colors of the halogens fade as they react to form the colorless compounds. Moving on to our fourth type of addition reaction, hydrohalogenation. Okay. Now, this is a type of reaction whereby you're going to have an alkene reacting with a hydrogen halide. Okay. Now, what are hydrogen halides? As the name suggests, these are compounds that contain hydrogen and a halogen. So, for example, hydrogen chloride, we have hydrogen and chlorine. Hydrogen bromide, we have hydrogen and bromine. Now, if I were to take any of these, react them with ethene, then this particular reaction is hydrohalogenation. Now, ethene is going to react with hydrogen chloride to form chloroethane. Okay? So, again, what will happen? Double bond will split open. And if it does so, you're going to have three single bonds. Hydrogen inaingia at one end, chlorine inaingia at the other. And you get your compound that is known as chloroethane. Now, what about if you get ethene and hydrogen bromide? You get bromoethane. Ethene and hydrogen iodide, you get iodoethane. Now, when it comes to the reaction of ethene with hydrogen chloride, it's very slow and it usually occurs only in the presence of a catalyst. When it comes to ethene with hydrogen bromide, it's more vigorous. But the reaction between ethene and hydrogen ion, this is the fastest of the three, okay? So it actually happens at room temperature. There's no need for a catalyst. Now you might be wondering why this is so. Now the reason is because you're going to have differing strengths in the bond between hydrogen and the halogen. Okay, so let me start with the hydrogen iodide. The bond between hydrogen and iodine in hydrogen iodide is the weakest, okay? So what happens is that when it reacts with ethene, it only needs just a little bit of energy for it to break down, to dissociate, and then react with ethene. So it makes this reaction more reactive. But if we take hydrogen chlorine, the bond between hydrogen and chlorine is the strongest. So for this to react, it needs quite more energy, and therefore it's slower to dissociate to form hydrogen and chlorine, which will then react with ethene. And that is the reason why the reaction between ethene and hydrogen chloride is the slowest, because the bond that is present in hydrogen chloride is the strongest of the three. Now, one thing, I don't want you to confuse hydrohalogenation with halogenation. When it comes to hydrohalogenation, what is happening is that in the compound that is formed, you are only going to have one chlorine atom, because the other atom that was added was hydrogen. But in the case of halogenation, because the compounds are essentially two, a molecule of halogen where you have two halogen atoms, you are going to end up having two halogen atoms being added onto the compound, okay? So, hapa ni mbili, hapa ni one. So, that is halogenation and that is hydrohalogenation. Moving on to the next reaction with bromine water. This is usually yellow in color and it has the following formula, HOBr. Now, if you were to take a gas jar containing ethane, add bromine water onto it and shake it, you're going to note that the yellow bromine water is going to be decolorized. It's going to turn colorless, okay? Now, this is because ethene reacts with the bromine water to form a compound called bromoethanol. This compound is colorless, and that is the reason why you are seeing a color change. You are seeing a change from yellow to colorless because the compound being formed is colorless. So, this is used as a test for alkene. If you want to find out whether a substance is alkene, use bromine water. If it's decolorized, then most probably alkene is present. Okay, so what happens during this reaction? Double bond in a split, of course, you're going to have two new single bonds. Now the bromine atom moves to one end, the hydroxide moves to the other, and you end up having this structure. Now, any structure, any compound that has the hydroxide group or H is an alkanol. So, in this case, this is ethanol because it has two carbon atoms. So, you're going to end up having bromoethanol. Our last reaction, and this is reaction with acidified potassium manganate 7. Now, if you bubble ethene into acidified potassium manganate 7, what will happen is that it's going to turn colorless. Now, potassium manganate 7 is purple in color, but in the presence of ethene, it is decolorized. It turns from purple to colorless. The reason is because potassium manganate 7 is reduced to manganese 2 ions, which are colorless. Now, let's talk about this, okay? Why am I talking about the solution being acidified potassium manganate 7? What do I mean? What do I mean by the term acidified? Now, for this particular reagent to be used, it needs to be acidified. How is it acidified? By adding a dilute acid. So, in most cases, the acid that is used is sulfuric acid. So, when you add dilute sulfuric acid to potassium manganate 7, you make it acidified. Okay? Now, potassium manganate 7 is an oxidizing agent. But if you were to add, if you were to acidify it, you make it an even stronger oxidizing agent, and therefore it will be able to oxidize alkenes. Okay? Now, for acidifying, sulfuric acid is usually used because it does not react with the oxidizing agent. If you were to use hydrochloric acid, it would react with acidified potassium manganate 7, leading to the formation of chlorine gas. We don't want that. So, acidification of potassium manganate 7 is carried out using sulfuric acid to make it an even stronger oxidizing agent. So, this allows it to oxidize alkenes. So in this particular reaction, the potassium manganate 7 is acting as an oxidizing agent because it oxidizes the alkenes. Now, in this case, it oxidizes ethene by adding oxygen at the double bond. Specifically, it adds the hydroxyl groups onto it, such that you end up forming a compound known as ethane 1,2-diol. Tulisema, any compound that has the hydroxyl group OH is an alkanol. So mwisho at the end of the name, you end up having ol. But in this case, how many hydroxyl groups do we have? We have 2. Where are they located? On the first and second carbon atom. Hence the name, ethane, because we have 2 carbon atoms, 1,2-diol. So in this case, if I'm talking about oxidation of the alkenes, that means that reduction is also going to take place. Remember redox, where reduction and oxidation occur simultaneously. If one species is being oxidized, then another is going to be reduced. So the alkene is going to be oxidized to form ethane 1,2-diol. Which is going to be reduced? The potassium manganate 7. So potassium manganate 7 is going to be reduced to manganese 2 ions and water. So the manganese 2 ions are colorless, and therefore that is the reason why potassium manganate 7 is decolorized by alkenes. So this, together with the use of bromine water, are 2 tests that are used to test for the presence of alkenes. And at this point, ladies and gentlemen, we are done with alkenes. When it comes to uses, you can just look those up. But yeah, tumemaliza with alkenes. I hope nimechafua ile mbaya, yeah? Yeah. So in our next lesson, we are going to discuss alkynes. See you there.